Power supplies are the unsung heroes of the electronic world. They might not be as glamorous as microprocessors or as eye-catching as high-resolution displays, but their role is absolutely crucial. Without power supplies, our smartphones, computers, and countless other electronic devices would simply be inert chunks of metal and plastic. Imagine a world without power supplies. Your phone wouldn't charge, your laptop wouldn't turn on, and your television would remain a dark rectangle. It's clear that these devices play a fundamental role in our technology-driven society. But what exactly is a power supply? In essence, it's a device that converts electrical energy from one form to another, typically from the alternating current supplied by the power grid to the direct current required by electronic circuits. This conversion process is essential because electronic components, such as transistors and integrated circuits, operate on a steady flow of direct current voltage. Power supplies act as intermediaries, transforming the raw, alternating current power into a stable and regulated direct current output that electronic devices can use. Switched-mode power supplies, or SMPS as they are commonly known, have revolutionized the world of electronics. These powerhouses of efficiency have become the go-to choice for a wide range of applications, from smartphones and laptops to industrial equipment and telecommunication systems. So, how do SMPS achieve their remarkable efficiency? The answer lies in their clever use of switching techniques. Unlike traditional linear power supplies, which rely on continuously dissipating excess energy as heat, SMPS employ high-frequency switching regulators to control the flow of power. By rapidly switching the input voltage on and off, SMPS can regulate the output voltage with minimal energy loss. This switching action is controlled by sophisticated electronic circuitry that monitors the output voltage and adjusts the switching frequency accordingly. The advantages of SMPS are numerous. Firstly, their high efficiency translates into less wasted energy, resulting in lower electricity bills and reduced heat dissipation. Secondly, their compact size and lightweight design make them ideal for portable electronic devices. Linear power supplies, while not as efficient as their switched-mode counterparts, still hold a prominent place in the world of electronics. They are known for their simplicity, low noise output, and ease of design. These power supplies operate on a straightforward principle, using a voltage regulator to maintain a constant output voltage regardless of input voltage fluctuations or changes in load current. The heart of a linear power supply is a pass transistor, which acts as a variable resistor, controlling the amount of current flowing to the output. A feedback mechanism monitors the output voltage and adjusts the resistance of the pass transistor accordingly, ensuring a stable output. While linear power supplies excel in simplicity, they do have some drawbacks. Their main disadvantage is their inherent inefficiency. Because the pass transistor operates in its linear region, it dissipates a significant amount of power as heat. This heat dissipation can lead to bulky designs and the need for heat sinks to prevent overheating. Despite these limitations, linear power supplies remain a popular choice for applications where low noise and ripple are paramount. The choice between an SMPS and a linear power supply depends largely on the specific application and its requirements. SMPS, with their high efficiency and compact size, are the preferred choice for a wide range of modern electronic devices. In portable devices like smartphones, laptops, and tablets, where battery life and size are critical considerations, SMPS reigns supreme. Their ability to deliver high power output in a small form factor makes them indispensable for these applications. In industrial settings, SMPS power everything from automation equipment and control systems to telecommunications infrastructure and medical devices. Their high reliability and efficiency make them well suited for demanding industrial environments. Linear power supplies, on the other hand, find their niche in applications where low noise and ripple are critical. Audio amplifiers, for example, often utilize linear power supplies to minimize unwanted noise that could interfere with sound quality. Section 5. Inside the box. A look at SMPS topology. The inner workings of an SMPS might seem complex at first glance, but understanding the basic topology can demystify their operation. At the heart of every SMPS lies a switching regulator, which is responsible for converting the input voltage to the desired output voltage. The switching regulator typically consists of a power transistor, an inductor, a diode, and a capacitor. These components work in concert to regulate the output voltage by rapidly switching the input voltage on and off. The switching process begins with the power transistor turning on, allowing current to flow through the inductor. The inductor stores energy in its magnetic field during this phase. When the power transistor turns off, the magnetic field collapses, inducing a voltage across the inductor. This induced voltage, along with the input voltage, charges the output capacitor, providing a smooth DC output. The diode in the circuit allows current to flow back to the input source when the power transistor is off, preventing voltage spikes. Section 6. Straight and narrow inside linear power supplies. Linear power supplies, in contrast to their switched-mode counterparts, employ a simpler and more straightforward topology. Their operation centers around a pass transistor, which acts as a variable resistor, regulating the output voltage. The pass transistor is typically a bipolar junction transistor, or BJT, or a field effect transistor, FET, operating in its linear region. In this region, the transistor's resistance varies proportionally to the input voltage, allowing it to control the amount of current flowing to the output. A feedback mechanism, usually implemented using an operational amplifier, or op-amp, monitors the output voltage and adjusts the base or gate voltage of the pass transistor accordingly. This feedback loop ensures that the output voltage remains constant, despite variations in input voltage or load current. While the simplicity of linear power supplies is advantageous, it comes at the cost of efficiency. Because the pass transistor operates in its linear region, it dissipates a significant amount of power as heat. This heat dissipation can lead to bulky designs and the need for heat sinks to prevent overheating. Section 7. Efficiency versus noise. The trade-offs in power supply design. When choosing between an SMPS and a linear power supply, engineers face a fundamental trade-off: efficiency versus noise. SMPS excel in efficiency, converting a high percentage of input power to usable output power. This efficiency stems from their switching mechanism, which minimizes power loss as heat. Linear power supplies, on the other hand, are inherently less efficient due to the power dissipated by the pass transistor. However, linear power supplies shine when it comes to noise performance. Their simple design and lack of switching elements result in very low output, ripple, and noise. This characteristic makes them ideal for applications where noise is a critical concern, such as audio amplifiers and sensitive measurement equipment. SMPS, while generally efficient, can generate high-frequency noise due to their switching operation. This noise can manifest as electromagnetic interference, or EMI, which can interfere with other electronic devices. Section 8. The future of power, trends, and advancements. The field of power electronics is constantly evolving, driven by the demand for smaller, more efficient, and more powerful power supplies. One prominent trend is the development of digital power supplies, which incorporate microcontrollers or digital signal processors, DSPs, for enhanced control and monitoring capabilities. Digital power supplies offer several advantages over their analog counterparts, including improved transient response, higher accuracy, and the ability to communicate with other systems. They also enable advanced features such as remote monitoring, fault diagnosis, and dynamic voltage scaling. Another area of innovation is the development of wide bandgap semiconductors, such as silicon carbide, SiC, and gallium nitride, GaN. These materials offer superior performance characteristics compared to traditional silicon-based semiconductors, enabling the design of power supplies with higher switching frequencies, higher efficiency, and reduced size. Section 9. Conclusion. Powering the future. From the ubiquitous smartphones in our pockets to the sophisticated industrial equipment that powers our modern world, power supplies play a vital role in our technology-driven society. Understanding the different types of power supplies, their advantages, and their limitations is essential for engineers and enthusiasts alike. As technology continues to advance, we can expect to see further innovations in power electronics, leading to even more efficient, compact, and intelligent power supplies. These advancements will undoubtedly shape the future of electronics, enabling the development of new and exciting devices that will continue to transform the way we live, work, and interact with the world around us.